Thank you all for joining us today. My name is Karim Mastoud. I am the manager of international projects at Premier Corex. So last session, we have had a very successful session, keeping it correct, the art of perfect preparation. It was a good turnout and was well received. So we're continuing with our technical webinars in 2026. This time we have Frank Zamora, who's our senior VP of fluids based in Houston. Okay. We will continue on with our schedule every 3 weeks. Okay. If you have any questions or requests, please feel free to email us, and we will respond to you. If you have joined these sessions before, welcome back. It's good to see some familiar faces. If this is your first time attending, thank you for joining us, and we appreciate having you on. Okay. Today's webinar is Rheology, Degradation Uncovered, and the key takeaways are over there. We're supposed to understand fluid and proppant behavior under real downhole conditions, learn how high-shear testing exposes fluid, proppant, and conductivity damage, gain actionable insights from Premier Corex workflows, and apply findings to optimize fracture design and well productivity. Just a few housekeeping rules. Please use the Q&A section of the panel to submit any questions at any time. We will answer them at the end of the session. Okay. The session is being recorded, and we will share the recording with the registered. The time is about 30 to 40 minutes, and then after that, we will give some time to the Q&A section. Okay. All attendees will remain muted during the webinar, so audio is not enabled. And this is Frank Zamora. So this is just a bit of bio about our speaker for today. He's joined Premier Corex in 2016 as a senior vice president and currently oversees operations in the US, as well as serving as the fluids subject matter expert. Frank brings 45 years of experience in the oil and gas industry, including senior leadership roles at FTSI, Trican, and Weatherford, okay, and nearly 27 years with Halliburton as well. He holds a bachelor's degree in electrical engineering from Texas A&M and a master's in engineering technology from Oklahoma State University. Frank is registered professional engineer in Texas and holds more than 50 industry patents. Okay, and we're very lucky to have you, Frank. Thank you very much. And with that, I'm going to hand over to you, and
all right. Well, thank you, Kareem. Thank you, Jennifer, for having me this morning. Can you hear me?
Yes, sir, we can.
All right. Very good. All right. Well, everyone, thank you. Well, good morning and good afternoon for everyone. Again, thank you for having me, and I appreciate everybody taking time from their busy schedules to listen to our presentation. So today we're going to talk about rheology degradation, and it's also in the form of a consortium we're putting together called FracTrue Consortium. And the way this thing was created, this goes back and ties very closely to another consortium that was put together by NSI called PEER Consortium, and PEER is Perforation Erosion Consortium. And so from this particular consortium, there was a discovery made. It wasn't the intent of the study, but the observations from that particular study motivated us to move in the direction of studying further the observations from that particular study. And one of the observations from that PEER Consortium, and this is a perforation erosion. So here are the pictures on the right. It was a large-scale study to simulate the actual effects of a fracture, of a real frac that would occur downhole. However, this was done at the surface, and this was in the middle picture here. You're actually seeing the simulator, which actually simulates the perforation, and in each one of these dampener goes a slot to simulate the actual perforation. So what we were observing from that is that two very critical things were being observed. One was that proppant does go through when injecting at frac rates, proppant does go under a severe particle degradation. Also saw that the viscosity of the fluid mixed at the blender was not the viscosity of the fluid after it went through the various perforations. And of course, this particular study investigated various flow rates, various velocities going through the perforations, perf sizes, various combinations and iterations to simulate those downhole conditions. And from that, we were seeing a constant of viscosity collapsing as it entered the perforation at these extreme shear rates of anywhere between 1,000 to 3,000 reciprocal seconds. So at the end of the day, what we're discovering is there are no frac models that were taking these observations into consideration when doing a frac design. So FracTrue was formed to basically quantify the effects to develop the next generation fluids and design grounded in high shear rate physics. So basically the overall outcome of this particular study is to really come up with new chemistry that is going to be high shear resistant type chemistry, which is currently not happening with the current technology that we have out in the market today. Yeah. So why it matters is that this shear degradation leads to unrealistic frac design. So you end up with polymer viscosities that are not actually doing any proppant transport. The effect of the proppant itself is not generating the conductivity that is being assumed from the proppant that was tested pre-frac. So let's take an assumption here that this is, of course, a model simulation of an actual frac design. So in this upper right-hand corner, assuming that your fluid viscosity is as what you assume it to be prior to closure, you would have a production outcome that is over here in the solid black line. And this is basically an example of how much losses you're going to end up with from what you thought was happening in the frac design versus what is actually might be happening in the frac design. So the upper right-hand corner is the actual frac design, assuming all parameters are as you assumed it to be in the inputs of your frac model. The bottom left-hand corner is the actual frac design after closure, which is the solid dotted black line. So you end up with a loss, some loss of roughly 18%. So let's assume now that the reality is that you're actually losing viscosity and proppant size. So the model would then predict that you're actually losing 28% from your original assumption. And at closure, you're losing as much as 42% simply because all the proppant is settled to the bottom. You have no proppant transport, therefore your frac length is no longer the frac length that we assumed it to be. And so you end up with a reduction of overall production, assuming a 100 mesh stand, which is a 7140 assumption. Now, the original measurements that we're doing are still very valid measurements to understand the fluid up to that perforated interval. So fluid that is going to be used from the blender to the downhole perforated interval is still valid in that you still have, in this example here, you have a polyacrylamide, an FR. This FR is a sheared degradable type fluid, so where you end up in the low end shear regime, you end up with higher viscosities than you do in the higher end shear regime. So this is one that goes from 0.1 reciprocal all the way to 1,000 reciprocal. And you can see that in a log scale, you would still have very good viscosity on the low end shear regime, and basically at the 511, you would end up with your conventional viscosity measurements. These numbers are still valid up to that perforation. As far as flow loop data, that is also still valid, and we know that these are right simply because we see that out on location. Whenever you pump an FR, you see the friction reduction from that polyacrylamide, and what that polyacrylamide is doing, it's taking a fluid that should be in turbulent flow and converting it more to a laminar flow regime, therefore reducing the overall friction caused by that turbulent flow. So we also measure in many cases how well the polymer hydrates. It has nothing to do with the friction properties in many cases. For example, if you were to run a polyacrylamide in a high brine or in a brine scenario, you would still say you would sacrifice the viscosity. However, you still have the effectiveness of changing that turbulent flow regime into a laminar flow regime, but viscosity is still a measurement, a means of measuring the polyacrylamide's hydration ability. So the flow loop is still a very good indicator of how well this fluid is converting a turbulent flow regime into a laminar to give us that friction reduction. However, over time, as you continuously flow this through the flow loop, you end up with still a degradation of that polymer. So that is another means. Now that we're going into these extended reach laterals, it's going to be important for us to understand how well that polymer is going to degrade in the tubulars itself. As far as polyacrylamides go, there's a difference between viscosity and elasticity. So in many of these HVFRs, many people or a lot of people buy these HVFRs and they want the physical properties of the HVFR simply because it has some elastic behavior. If you add enough polymer to the fluid, it develops a network that allows these fluids to have some elasticity. So for example, you have, in this particular case, a 15-pound linear gel. You can see that in that 15-pound linear gel, it's not very easy to see here, but I'll go ahead and accelerate it. As you accelerate it, you can see that the viscous fluid, even though the 15-pound gel and the 3 GPT HVFR have the same viscosity, you're going to see that the overall settling rate of that 4070 sand is going to be right there at the immediate wellbore. So in the case of an HVFR where you have elasticity over time, as you pumping the HVFR, you end up with elastic behavior. And this is the difference between viscosity and elasticity, in that you have very good proppant transport characteristics that go further out into the fracture, or at least that was the initial assumption. Now that we're starting to investigate the shear effects beyond the perforation, on the other side of the perforation, this is part of what we're trying to understand is, do we lose that elastic behavior once it goes through the high shear regime of anything over 100,000 reciprocal seconds? Another major parameter is the proppant conductivity. We measure proppant conductivity to really determine the quality of the overall proppant, determining the sphericity, determining the particle size distribution. All of these are characteristics of the sand or the proppant to fully understand how well of a conducive path it's going to create once proppant is placed in the fracture. So what we end up seeing here in many cases is because here in the United States, we use a lot of native sand versus what used to be called northern white sand. One sand being a little more angular than the other, one being a little more spherical. We end up where we see in many cases on the low closure pressures. Now, this is not going to be the same case, in every native versus northern white. This is just an example here of a study that we did a few years ago to determine the conductivity values of a native sand versus a northern white sand. And what we discovered is that for this particular case, in the low pressure closure pressure area, the two proppants are very similar in conductivity, as well as very similar in conductivity on the high closures at 9,000 psi, where many sands actually go catastrophic. So in this particular case, we're seeing that effect right at about 7,000 psi, where the closure or the conductivity values are starting to come together simply because the sand is becoming a little catastrophic at closure pressure, therefore creating a very similar sand across that conducive path. The difference is going to be between the 2,000 and 7,000 psi closure, and those are numbers that reservoir engineers need to take into consideration as they're predicting their overall production of the reservoir as to how long is it going to take for the reservoir to go between 2,000 psi closure versus 7,000 psi closure. And that's where the difference of the sphericity, particle size distribution come into effect in determining or understanding the performance of the overall proppant. These numbers are the pre-frac numbers. However, as we observed in the peer consortium, is that some of this proppant in the native sand side, where you have a lot of angularity, the proppant is undergoing some degradation as well. Now, the big problem is that we're making the assumption that the overall frac design is using parameters that are actually pre-frac. However, what's happening post-frac in the actual perforation, or as it goes through the perforation, we're losing a tremendous amount of viscosity. The proppant is being destroyed and degraded over time, therefore affecting the overall conductivity of the proppant itself. So now our actual realistic frac model is not anywhere near where the original assumptions were made. So these are the questions that basically are driving the frac true investigation plan. And as I mentioned earlier, these are the some of the shear areas that we're taking into consideration. One of these, of course, the surface equipment goes through some shear, the well bore, and we know that those numbers are fairly close to the overall measured numbers that we do in the lab itself. However, fluids that go through the actual perforations, no one's really looked at or investigated what those parameters are after the fluid undergoes that particular process, affecting the overall fracture and conductivity values. So at the end of the day, we're basically the customer, the operator, is seeing a significant loss in production. And these are the things that we're trying to bring to a better understanding. Now, this problem of shear degradation is not something that we just recently came up with. There is a paper that was written by SNF that also investigated the effects of shear on their polyacrylamide. And here, for your particular reference, is the actual paper reference number for your edification. So the observations that were made on location while they were doing the large-scale peer study, we discovered two things. And of course, these parameters or these numbers, these viscosity numbers, were measured at 30 degrees F. a very cold day in Utah when the study was actually done. Therefore, these numbers in ambient condition and room temperature are even going to be lower. So using the Grace 3600 rheometer at 300, measuring the viscosity at 300 RPM with a B1 bob at 511 reciprocal seconds, we're starting off with fluid viscosities of 3 centipoise and above. And in many cases, or in just about every case, we're seeing viscosities less than 2 centipoise. And in most cases, we were sitting over here in the 1 centipoise. So we were degrading the polymer significantly once it went through the actual perforation itself. Another observation that was seen was as we were capturing the fluid, the FR, in a 5-gallon bucket to clean out the next test, we were discovering that these sand particles were basically agglomerating and creating these little colloids were actually agglomerating with the polyacrylamide, and they were very, very difficult to separate. If we were to add another component in here called ferric iron, which is the Fe3, in many cases, what we would then have is a very nice, stable little gummy bear that would, in many cases, a lot of people call it goo gummy bear, but it's a cross-linked polyacrylamide that is very, very stable, and these solids would add more stability to the overall problem. So here's the observation on the proppant itself. So the blue graph, the blue bars are the actual 4070 sand that was measured pre-treatment. So you can see a nice, basically a good range from 40 to 120. So the blue line or the blue bars represent the pre-treated proppant. The orange bars represent the proppant that was captured after it went through the perforation. So what we're seeing is a lot of the bigger size particles, the bigger angular particles, were actually being broken up into smaller particles, and those smaller particles were showing up in the 100 and 120 mesh. Now there's probably an additional mesh sizes over here that we did not measure, not thinking about this. This is kind of like a thought after the fact. Had we measured the 140, 170, 200 mesh, those curves would have been out here as well, simply because they didn't exist in the original proppant measurement, but they would have existed on the post-treatment sieve analysis. So what happens here in this particular case is that we're generating additional turbidity to the overall fluid. So you start off with a proppant that has a 360 NTU measurement in the turbidity, and you end up with turbidity numbers that could exceed, that could be, sorry about that, that could be as much as, 4,000 NTUs. And what happens here is the only thing you need to be concerned about is whenever you generate a lot of turbidity in your fluid, is that all this surface area is basically going to consume your chemistry. So whenever you have a very turbid material, you're going to end up consuming, if you're adding surfactants or you're adding biocides or whatever it may be, this surface area could possibly consume some of your chemistry, neutralizing it so that its effectiveness or the purpose of its addition is no longer beneficial. So here is an actual settling test of something that has got high turbidity with a polyacrylamide. You can actually see the agglomeration, the flocculation that takes place whenever you have, what happened? Whenever you have colloids, and colloids are particle sizes anywhere between 1 nanometer in size up to 1,000 nanometers in size. They call that a colloid. a very small particle, and these small particles, they like to flocculate. And FR is a flocculant. Therefore, these polyacrylamides that are highly charged, they will have a tendency to want to agglomerate these little colloids together, creating a nice little big ball of particles that are very, very stable or could possibly stabilize the FR. Therefore, even though you're adding breaker or you're adding temperature to the overall system, it's quite possible that the polymer may not be exposed to all of that energy needed to break it apart or break the backbone, and you end up with proppant flow back as well as still a viscous material that is bringing additional proppant back to location or back to the surface, creating surface issues. The system is very slow here. So what we've been able to develop from here is that, okay, these were nice observations out on location. How can we bring this back into the laboratory and try to further investigate how to simulate what we saw out in the field? So the first calculation, of course, is the shear rate that goes through the actual perforations. And so Dante Guerra, who basically put peer consortium together, have come up with these graphs that make it a little simple, or makes it easier to make those calculations, where depending on the perforation size and the actual pressure that you will number perforations that may be taking fluid, you can come in here and determine what that shear rate needs to be per perforation exposure. So once we understand what that perforation exposure is, then we can actually go into the lab and simulate and we're focused on the apparent viscosity being 8 times the velocity of the fluid going through the perforation divided by the diameter of the actual perforation. So this is the number of interest that we're actually doing or investigating in the lab. So here's the simulator to actually simulate that shear rate through the perforation to understand the effects on the actual polymer. Now, this study is not only going to take polyacrylamide or FRs into consideration, it's also going to investigate the natural polymer, the guar, the HPG, the CMHPG, the derivatized guar systems, so the cross-link systems. So the whole premise here is to get a better understanding of the entire fluid system, not just the polyacrylamide, but to include the natural polymers and the cross-link polymers along with that, linear as well as cross-link. So what we have here is a 1 liter sample, and we have a simulated perforation, and based on how fast we want to actually simulate the shear rate viscosity, this particular example is of 164,000 reciprocal seconds. So it takes approximately 1.5 seconds to actually put the fluid through this orifice, capture the fluid. That was 1 liter that just passed through that orifice. Now we can take and collect that fluid, take it to the lab, and do the viscosity measurements on that. Here's an example of 250,000 reciprocal seconds. At 250,000 or 45,000, it took right at 1 second to actually pump 1 liter of fluid through the orifice to simulate 250,000 reciprocal seconds. So now we have the ability in the laboratory to simulate those viscosity changes depending on what that shear rate viscosity is going to be. So the bigger the perforation, or depending on what your fluid rate is, we can then simulate that in the laboratory. All right, help me out here. Okay, so here is the actual graph from the actual field study on location. We have an HVFR in a particular fluid that generated this shear rate curve from 1 to 1,000 reciprocal seconds. So this was the baseline. The fluid that was captured on the other end, however, was 1 centipoise. So here is the 1 centipoise mark. So a little over one, between 1 and 2 centipoise. So what we were seeing out in the field was approximately 245,000 reciprocal seconds. That study that Dante was doing out in Utah was generating a shear effect of approximately 250,000 reciprocal seconds. And so now we were able to simulate that here in the lab. And this here is 164,000. So basically what we're doing is this is the amount of viscosity loss as from the actual original measurement versus the post shear measurement. In the low end shear regime, we're losing as much as 80 to 90% of that viscosity. At the 511 reciprocal seconds, we're losing as much as 60 to 70% reciprocal, 60 to 70% centipoise in viscosity. So again, by introducing this particular study that we're going through, the fracture consortium is basically to develop a database and a modeling framework that describes what the fluid and the proppant performance is going to be under realistic high shear fracturing conditions. This will allow us a better understanding for modeling purposes and better prediction purposes. So the overall areas of investigation, of course, going to be proppant transport, to try to understand the proppant inertial effects as it's going through the various perforations, so that it would be, kind of a perf by perf partitioning, to study the shear damage to the fluid viscosity based on various concentrations of FR. How does adding more FR affect the overall viscosity going through those high shear rates? Various types of FRs. Can we develop in working with suppliers to come up with a better fluid system if technology is going to keep us in the polyacrylamide arena? Can we develop, or can suppliers develop a better friction reducer that will withstand the high shear regimes? How does the sand, how does the proppant, how do the various types of proppants get affected through the high shear regime depending on mineralogy? Does mineralogy, is that a measurement that can be taken to better understand how well the proppant is going to resist shear damage? And again, like I said, we're going to study the HVFRs, the FRs, linears and cross-linked fluids, and then run a series of, at the end of the day, when an operator buys a frac job, he's not buying a frac job just simply to put the job away and call it a success. The overall premise of actually purchasing the frac and putting the job in the ground is to get the actual frac design that the customer thought he was getting with regards to proppant transport, fracture height, fracture width, the amount of conductivity and proppant far out into the far field. All of these things need to be taken into consideration to be considered a successful frac job. So there'll be a series of conductivity tests that will be run post and pre-treatment to understand what those effects are on conductivity itself. And then again, to help understand the development of these gummy bears, if we're going to stay in the polyacrylamide, highly charged polymer, then it's going to be important to fully understand how to prevent this cross-linked polyacrylamide with ferric iron from causing production damage or damage to the production facility. And at the end is to basically develop an empirical, analytical, numerical modeling method to predict what that particular polymer or how that particular polymer will perform under these shear conditions. And of course, to try to integrate it with STEM plan with the effective viscosity correlations. So part of this study is to develop models like this that don't currently exist, where we're going to end up with a acrylic model that we could actually visualize how this proppant is being transported through a horizontal wellbore in various cluster fields to determine how much proppant from an inertial effect, how much proppant actually makes the turn here at the immediate heel area versus how much proppant is being transported down into the toe. And I think I have this model kind of backwards because the inertial effects should be toe bias rather than heel bias. However, as a cartoon image, this is the idea on what we're going to investigate with respect to proppant transport and the inertial effects on that proppant transport. And again, to further investigate the post-frac and the pre-frac conductivity, how badly are we damaging that proppant and how well is that conductivity going to survive going through that particular shear, as well as understanding what the mineralogy is going to be like in each one of the proppants that are being studied, to understand whether a high quartz content versus any of these other silicate contents will affect the overall performance as far as shear resistance is concerned. To further understand this gooey material that is being produced in many cases and better understand how this ferric iron and the polyacrylamides and a polyacrylamide that has undergone a tremendous amount of shear and has been basically cut into millions of pieces, how that cross-linked material or how that material gets cross-linked with ferric iron, and is that one of the reasons why this goo is actually so stable in many cases? So again, the whole premise of this fracture consortium is to basically provide an industry-based group of individuals and companies, service companies, suppliers, and operators to bring their ideas together to better come up with better chemistry and better testing protocols to help understand the performance of the overall chemistry and proppant, as well as the outcomes on the conductivity side, to basically provide the customer a better producing well. So these want to thank the peer consortium for allowing us to participate in that phase of the overall project. And these are the current members of that peer group. So definitely want to thank Dante Guerra, the president of NSI, for basically allowing us to participate in this particular project to the point where we can better understand the degradation of the polymer, the degradation of the overall proppant, and come up with some conductivity data to better understand what the outcome of the overall frac is going to be. But I have one more slide here, but I guess.
Thank you, Frank, very much. That was quite interesting. I'm going to take control back. Okay. That was quite interesting. Thank you very much and very insightful. So for the attendees, if anyone has any questions, please go ahead and post your questions on the Q&A section. I think we already have some questions in the chat comments, so I'll go through those. So Frank, great presentation. Thank you. What was the chemistry of the FR you presented today, or were there different FRs in your study? Have you looked at the impact of changing the FR chemistry as well as changing the mud weight of the FR, MW of the FR?
Yeah, so in this particular study, okay, so this particular study only investigate, again, remember, this was a afterthought after we had actually run the original design. This was only one particular FR that was used in this particular study. The premise of the study, of course, is to study the perforation erosion effect. However, after looking at this, the next phase of the peer group is to hopefully, with this particular study undergoing or going through its original phases, by the time the next phase gets pumped in peer, that there will be an FR that has undergone various studies and tests, that particular FR can then be used in the next phase of that particular project. However, for right now, this particular study only investigated the one and only FR, the one and only HVFR that was provided by one of the suppliers.
Okay, thank you, Frank. There's another question. This is also, will your study keep the active content of the FRs constant? Will the group study DPAMs, slurries, and EPAMs, and the impact of additional chemistry in the frac fluid, i.e. scale corrosion, biocide, clay inhibition, stabilizers, and so on?
Yeah, the beauty about this is that, yes, we will have that ability to do that, to determine what the shear effects are of the polymer and the overall chemistry as a whole. But that was not done here. This was simply a polyacrylamide test with sand. But we now have the ability in the lab to simulate what actually took place. Therefore, any combination iteration of the test that we can come up with as a collective, just determine, hey, the consortium needs to really investigate this as an important characteristic, then we can focus on that, assuming the group as a whole is agreeable to moving forward in that direction.
Okay, thank you, Frank. Thank you very much. Don't see any other questions have come through just yet. Okay. But if anyone thinks of any questions, yeah, please do let us know or email us, and we'll be more than happy to answer any questions that you might have. Okay. So with that, I'd like to well, acknowledge Frank. Thank you for the excellent presentation and the response to the question. For everyone, you will receive a link with the recording, so look out for that. And just to let you know, our next session will be held on the 3rd of February. So the speakers are very own Sean Parker, a technical services manager based in Houston. Sean will be talking about the fracture conductivity evolution under shear conditions and chemically realistic conditions as well. So please feel free to register for that event, 3rd of February. Follow our LinkedIn page for more updates on our technical webinars, and join our website. The recording will be also available on our YouTube channel. Okay. Thank you all for your participation, and I hope this was insightful to you.
All right. Well, thank you, everyone, and thank you for your time.